It is generally recommended to adhere to the 60 degrees Celsius ampacity rating for cables exceeding 1/0 American wire gauge, even when the cable possesses a 90 degrees Celsius rating. The ampacity of a cable is influenced by several factors, including conductor material and size, cable insulation type, ambient temperature, and connector temperature rating. In the context of cables larger than 1/0 American wire gauge, the temperature rating of the connector often emerges as the limiting factor. Connectors are engineered with specific maximum operating temperatures. Due to the larger dimensions of conductors above 1/0 American wire gauge, the connectors employed are commonly rated for a maximum of 60 degrees Celsius. The National Electrical Code stipulates that the ampacity of a cable must be determined based on the lowest rated component within the circuit. Consequently, if the connectors are rated for 60 degrees Celsius, the cable's ampacity must align with the 60-degree rating, irrespective of the cable's 90 degrees Celsius rating. Information pertaining to connector temperature ratings can typically be found in the manufacturer's specifications or directly on the connector itself. It is critical to accurately determine ampacity ratings for all components within an electrical circuit to ensure both safe and reliable operation. The ampacity of a conductor dictates the maximum current, measured in amps, it can carry without exceeding its temperature rating. This rating is essential for preventing overheating and potential fire hazards. The National Electrical Code, or NEC, provides tables that specify ampacities for various conductor types and sizes, taking into account factors like insulation temperature rating and ambient temperature. These tables are essential for selecting the correct wire size for a given electrical load. When dealing with conductors larger than 1/0 American wire gauge, a common practice is to use the 60 degrees Celsius ampacity column in the NEC tables, even if the conductor's insulation is rated for a higher temperature, such as 75 degrees Celsius or 90 degrees Celsius. The primary reason for this practice is that the terminals and connectors used with these larger conductors are often only rated for 60 degrees Celsius. Therefore, using the 60 degrees Celsius ampacity ensures that the entire system, including the conductor and its terminations, operates within safe temperature limits. The NEC mandates that electrical installations adhere to the temperature limitations of the lowest rated component in the circuit. This means that if a conductor is rated for 90 degrees Celsius but its terminations are only rated for 60 degrees Celsius, the 60 degrees Celsius ampacity must be used. This requirement is in place to prevent overheating at the terminations, which can lead to insulation breakdown, loose connections, and potentially electrical fires. The temperature rating of a connector or terminal indicates the maximum temperature at which it can safely operate while carrying its rated current. Exceeding this temperature can degrade the connector's material, reduce its conductivity, and increase the risk of failure. Connector temperature ratings are typically marked on the connector itself or can be found in the manufacturer's specifications. It's crucial to select connectors that are appropriately rated for the conductor size and the expected operating temperature of the circuit. There are situations where higher temperature rated connectors are used with larger conductors, allowing the use of the conductor's higher ampacity rating. However, these connectors are typically more expensive and may require specialized installation procedures. In such cases, it's essential to verify that all components in the circuit, including the conductor, connectors, and any other devices, are rated for the same temperature and that the installation complies with all applicable codes and standards. Ambient temperature also plays a significant role in determining conductor ampacity. The NEC ampacity tables are based on specific ambient temperatures, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the actual ambient temperature exceeds this value, the conductor's ampacity must be derated to account for the increased heat. Derating involves reducing the allowable current carrying capacity of the conductor to prevent it from overheating in a high ambient temperature. Derating factors are provided in the NEC and are based on the conductor's insulation type and the difference between the actual ambient temperature and the table's base temperature. Proper conductor sizing and ampacity calculations are essential for ensuring the safe and reliable operation of electrical systems. Failing to account for factors like connector temperature ratings and ambient temperature can lead to overheating, insulation breakdown, and potentially hazardous conditions. Consulting the NEC and following manufacturer's instructions are critical for proper electrical installations. In summary, firstly, for conductors larger than 1/0 American wire gauge, the 60°C ampacity rating is often used due to the temperature limitations of the connectors. Secondly, the NEC requires that the lowest rated component in the circuit determines the overall ampacity. Thirdly, connector temperature ratings can be found on the connector itself or in the manufacturer's specifications. Fourthly, ambient temperature must be considered when determining conductor ampacity, and earthing may be necessary in high temperature environments. Always consult the NEC and follow manufacturer's instructions for proper electrical installations. Now let's delve into the specifics of ampacity adjustments and corrections, as these are crucial aspects of electrical installations that must be carefully considered to ensure safety and compliance with the National Electrical Code, or NEC. Ampacity adjustment, also known as earthing, is the process of reducing the allowable current carrying capacity of a conductor to account for factors that increase its operating temperature. These factors include high ambient temperatures, multiple conductors in a raceway or cable, and the presence of harmonics in the electrical system. The NEC provides tables and formulas for calculating ampacity adjustment factors, which must be applied to the base ampacity of the conductor to determine its adjusted ampacity. High ambient temperatures can significantly impact the ampacity of a conductor. The NEC ampacity tables are based on a specific ambient temperature, typically 30°C or 86°F. If the actual ambient temperature exceeds this value, the conductor's ampacity must be reduced to prevent it from overheating. The amount of ampacity reduction depends on the conductor's insulation type and the difference between the actual ambient temperature and the table's base temperature. The NEC provides ampacity correction factors for various insulation types and temperature ranges, which must be applied to the base ampacity to determine the corrected ampacity. For example, if a conductor with a 90°C insulation rating is installed in an ambient temperature of 50°C, its ampacity must be reduced by a certain percentage, as specified in the NEC tables. This reduction ensures that the conductor's operating temperature does not exceed its insulation rating, preventing insulation breakdown and potential fire hazards. When multiple current-carrying conductors are installed in the same raceway, cable, or enclosure, their ampacity must be adjusted to account for the increased heat generated by the conductors. The NEC specifies ampacity adjustment factors based on the number of current-carrying conductors in the raceway or cable. These adjustment factors reduce the allowable current for each conductor to prevent overheating. The more conductors in a raceway, the greater the ampacity reduction. For example, if there are 4 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced to 80% of its base ampacity. This adjustment ensures that the total heat generated by the conductors does not exceed the raceway's or cable's ability to dissipate heat. It's important to note that neutral conductors that only carry the unbalanced current from other phase conductors are not typically counted as current-carrying conductors for ampacity adjustment purposes. However, if the neutral conductor carries a significant amount of harmonic current, it must be considered a current-carrying conductor for ampacity adjustment. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices and other nonlinear loads. These currents can cause overheating in neutral conductors and other electrical equipment. If an electrical system is known to have a high harmonic content, the neutral conductor should be oversized or other measures should be taken to mitigate the effects of the harmonic currents. Ampacity correction, also known as voltage drop compensation, is the process of increasing the size of a conductor to compensate for voltage drop. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor's resistance, the length of the conductor, and the amount of current flowing through the conductor. The NEC provides formulas and tables for calculating voltage drop. If the calculated voltage drop exceeds the recommended limits, the conductor size must be increased to reduce the voltage drop. Increasing the conductor size reduces its resistance, which in turn reduces the voltage drop. In some cases, it may be necessary to install a separate feeder or branch circuit to reduce voltage drop. This is especially true for long runs of conductors or for circuits that supply high current loads. Proper ampacity adjustment and correction are essential for ensuring the safe and reliable operation of electrical systems. Failing to account for factors like high ambient temperatures, multiple conductors in a raceway, and voltage drop can lead to overheating, equipment malfunction, and potentially hazardous conditions. Consulting the NEC and following manufacturer's instructions are critical for proper electrical installations. In summary, firstly, ampacity adjustment, or directing, is the process of reducing the allowable current carrying capacity of a conductor to account for factors that increase its operating temperature. Secondly, high ambient temperatures and multiple conductors in a raceway can require ampacity adjustment. Thirdly, ampacity correction, or voltage drop compensation, is the process of increasing the size of a conductor to compensate for voltage drop. Fourthly, the NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Always consult the NEC and follow manufacturer's instructions for proper electrical installations. Let us explore the critical aspects of selecting the right types of conductors for electrical installations, as it is a fundamental aspect of electrical engineering and safety. The selection of appropriate conductors is determined by several factors, including the application, the operating environment, the current carrying capacity, and the voltage requirements. The National Electrical Code, or NEC, provides comprehensive guidelines and specifications for conductor selection to ensure safe and reliable electrical systems. Conductors are typically made of copper or aluminum, each having its own advantages and disadvantages. Copper is a highly conductive material with excellent corrosion resistance and ductility. It is widely used in electrical wiring for residential, commercial, and industrial applications. Aluminum is a lighter and less expensive alternative to copper, but it has lower conductivity and is more susceptible to corrosion. Aluminum conductors are often used in overhead power transmission lines and in some types of building wiring. The NEC specifies the allowable ampacities for different conductor types and sizes based on their insulation temperature ratings and installation conditions. Ampacity is the maximum current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The NEC ampacity tables are based on specific ambient temperatures and installation methods. If the actual ambient temperature exceeds the table's base temperature, the conductor's ampacity must be derated to account for the increased heat. Conductor insulation is a critical factor in determining its suitability for a particular application. The NEC recognizes various types of insulation, each with its own temperature rating, moisture resistance, and other characteristics. Common insulation types include THHN, THWN, THW, XHHW, and RHW. THHN insulation is a thermoplastic high heat resistant nylon coated insulation commonly used for general purpose wiring in dry locations. THWN insulation is a thermoplastic heat and water resistant nylon coated insulation suitable for both wet and dry locations. THW insulation is a thermoplastic heat and water resistant insulation also suitable for wet and dry locations, but it has a lower temperature rating than THHN or THWN. XHHW insulation is a cross-linked polyethylene high heat and water resistant insulation with excellent electrical properties and is suitable for both wet and dry locations. RHW insulation is a rubber heat and water resistant insulation commonly used for underground wiring and other wet locations. The NEC specifies the allowable uses and installation methods for each type of insulation. It is important to select the appropriate insulation type based on the operating environment and the potential for exposure to moisture, chemicals, or high temperatures. Conductor size is another critical factor in conductor selection. The NEC specifies the minimum conductor size for various applications based on the load current and the allowable voltage drop. The conductor size is typically expressed in American wire gauge, or AWG, for smaller conductors and in circular mils for larger conductors. The larger the AWG number, the smaller the conductor size. For example, a 14 American wire gauge conductor is smaller than a 12 American wire gauge conductor. The NEC provides tables that specify the allowable ampacities for different conductor sizes based on their insulation type and installation conditions. It is important to select a conductor size that is large enough to carry the load current without exceeding its ampacity rating. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor's resistance, the length of the conductor, and the amount of current flowing through the conductor. If the calculated voltage drop exceeds the recommended limits, the conductor size must be increased to reduce the voltage drop. Grounding conductors are used to provide a safe path for fault currents to return to the source. The NEC specifies the minimum size for grounding conductors based on the size of the ungrounded conductors in the circuit. Grounding conductors can be bare or insulated and are typically made of copper or aluminum. Equipment grounding conductors are used to connect the metal enclosures of electrical equipment to the grounding system. This helps to prevent electric shock hazards by providing a low impedance path for fault currents to flow back to the source, tripping the circuit breaker or fuse and energizing the equipment. Bonding conductors are used to connect different metal parts of the electrical system together to create a continuous electrical path. This helps to reduce the risk of electric shock by ensuring that all metal parts are at the same potential. In summary, firstly, conductors are typically made of copper or aluminum, each having its own advantages and disadvantages. Secondly, the NEC specifies the allowable ampacities for different conductor types and sizes based on their insulation temperature ratings and installation conditions. Thirdly, common insulation types include THHN, THWN, THW, XHHW, and RHW, each with its own temperature rating, moisture resistance, and other characteristics. Fourthly, the NEC specifies the minimum conductor size for various applications based on the load current and the allowable voltage drop. Always consult the NEC and follow manufacturer's instructions for proper electrical installations.